We had seen individual samples as vectors. Let us understand the data or the set of such samples as a matrix. The idea is very simple. We construct a matrix out of all the samples that we have such that each column is a sample. So if each sample is in D dimension and we have n samples, we can consider this as a matrix X as a matrix of D by n. This is quite straightforward, but this matrix sometimes has a lot of interesting insights. Let us start with a simple case of say all the samples are identical. So your X matrix is x1, x1, and x1, n times just repeating. It does not add any new information. Like the first sample is x1, then the other samples are not really adding any new information. We obviously know that x is of rank 1. The rest of the columns are linearly dependent on the first one. It's actually multiple of 1. What about if you have a set of samples, say on this line? So we look at a matrix now in 2 dimension, say D is equal to 2. The samples are 1, 1, 2, 2, 3, 3, 4, 4, 10, 10, 20, 20. There are say 6 samples in 2 dimension, but the rank is still 1. The rest of the columns are multiple of this. Just this reminds us that it is possible that though the data is in really large dimension, the data could be lying in only a small subspace. Let us take 2 examples. We look at a set of measurements of say temperature and volume, keeping the pressure constant. From the school physics, we know that there is a linear relationship between these and the samples should be on a line. Or we go to a school and look at the height and weight of the children in certain age range and try to plot it. If you carefully watch these 2 situations, we realize if we had taken measurements of temperature and volume with some sensors, which may have noise, which may have measurement errors, we will be getting this property with some amount of noise. In practice, your data has a noise. However precise is your physics or the properties that we have here, there is a noise which possibly may deviate the samples from the line. Or if you look at the height-weight relationship of this, it is not clear that there is a very well defined relationship between height and weight, but we know that when the height increases, weight increases in general. And the samples are around a line. So there is a property, there is a relationship, and you start to see samples which are around that property. Now what this will reflect on our data matrix of say 2 by 6 that we have taken from this situation or this situation. You realize that if you numerically compute, your rank may not be 1. But the rank of this matrix is practically close to 1. The rest of it is coming from the deviation of the data from that property that we are interested in. So you will see soon that your data matrix need not be rank deficient, but it is practically rank deficient. And this property will be of immense use to us.